Hello everyone. So I'll start the discussion on probability and stats from this session onwards. So let's start with a story, okay? And then we'll see why the probability and stats is being used. A patient is being admitted in a hospital. So there's a patient, okay? He has got some disease and he's admitted to the hospital. And then what happens is now he is accompanied by some relatives. There are some relatives whom he's accompanied by, and then he's being hospitalized. So the relative and the nurse are having some conversation. I want you to focus on the conversation they are having. Okay, the relative asks the nurse a question. So what's the question he asks? He asks, nurse, what is the probability that the drug will work? So the drugs that you have given to the patients, so what's the probability that it will work? Nurse says, I hope it works. We'll know it tomorrow. Okay. Then relative again comes. He says, yes, but what is the probability that it will? Give me the probability that it will. Nurse says, each case is different. We have to wait for tomorrow and we'll see it. Then again relative asks a question. But let us see, out of 100 patients or 100 patients that you treat under similar conditions, the conditions that my patient has or my relative has, under these conditions, if you treat 100 patients, how many times would you expect the drug to work? Nurse is now somehow annoyed and she doesn't know how to answer. She said, I told you every person is different. For some it works and for some it doesn't. Again, relative he insists because he's a mathematical guy like us. So he says, no, no, tell me if you had to bet whether it will work or not. So which side will you bet on? Will you bet that it will work or will you bet it will not work? Then nurse a little bit like again annoyed and she said, I'll bet it will work. Now the relative is somehow relieved that oh, she at least said that the drug will work. Now the relative asked a question to confirm like this drug will really work. She said, are you willing to lose $2? Are you willing to lose $2 if it works? And are you ready to lose $2 if it does not work? If it does not work, and are you willing to win $1 if it works? Okay, now he just gave him some bet. He said, okay, as you are saying that it will work, so are you willing to lose $2 if it does not work? And if it works, I'll give you $1. The nurse said, what a sick thought, you are wasting my time. So from this story, you're seeing that in day-to-day conversations, we're using probability a lot. Okay, uncertainty, and when we don't know a thing, we say probably it will happen, it's likely to happen, and terms like these will appear. If you see, a lot of terms like this will appear. So from this story, if you know that the whole world, the whole life of yours that you have been seeing is more or less uncertain. Okay, there is no certainty in every case, and most of the things that you see around the world, they are uncertain. Let's suppose you have to go to college and you want to know the weather. It's uncertain. So what sort of weather it will be tomorrow? There is high uncertainty in that. And if you have to do a certain task and your whole day even is uncertain, if you if you have a look on today that you did today, and most of these things were not planned and there was uncertainty. Maybe there was some structure or some certainty, but most of these things were uncertain. Now what is this probability doing? So probability basically captures this uncertainty. Okay, how many of this can relate with the story? Okay, so this story basically happened in day-to-day life, and we wanted to model it perfectly. So when you are saying to the doctor, doctor, will this drug work? Doctor, will I be fine? Or something like that. And even you can ask me question, sir, will we get the job after learning this? So then I'll basically have to make a probability model. Okay, so what is probability? Now in nutshell, I'll write the definition of probability. Okay, so what is probability? So probability, it basically captures uncertainty. So captures uncertainty. So when we have some uncertainty, so it captures and makes a mathematical model, and it gives us a mathematical model to deal with this uncertainty. Okay, captures or deals with uncertainty. Okay, how to deal with this uncertainty, what will happen? So it quantifies the uncertainty, if you ask me. And usually the life and the world is messy. Okay, it operates on uncertainty. That's why we have to model it. And probability basically quantifies this belief. So I can say it captures, deals with uncertainty, and quantifies it. And quantifies it. Quantifies means giving a metric to it. Okay, so in short, I can say probability theory is mathematics of uncertainty. So probability theory is mathematics of uncertainty. I hope this is clear. Now let's see, is uncertainty normal? Okay, that's the first thing I want you to have your focus on, uncertainty. That's where probability arises. Okay, if you know everything till a certain level, then you don't need the probability. So basically what uncertainty refers, it refers to the incomplete information. Okay, if you are doing something, if you do not have a complete information about that, and you refer that thing as uncertainty. And much the mathematics is basically focused with logic, and in programming, computer programming, or the things that you do, some of them are sort of certain. For example, you write program, so you know what will this program do. First line will be this, next line will be this, third line will be this. So it's something deterministic path. Okay, everything will be executed deterministically, but yet there are some things which are uncertain, like that you don't know, there is a lot of hardware noise. Okay, hardware noise is there, and you have to deal with the hardware noise. There are some errors which has been checked. If you are from most of you are from computer science background, you know that when you even send the packets, you do some error checking. Okay, some crcs, Hamming codes, and these things are there, we check for the errors. Okay, so certainty is not perfect, so our information is not even perfect. So everything that you deal, some of them are deterministic, you code a thing that is deterministic, but most of the things they have uncertainty. Okay, so if you have even heard these terms, luck, chance, odds, likelihood, risk, so all these things basically give you the hint that there is some uncertainty. So I'm saying, oh, he got very lucky. So what is the meaning of that? Because we did not know the deterministic path that will happen, deterministic thing that will happen. And then if the odds were in his favor, right now I said odds again. Okay, and if something happened in the favor of a person, we said he got lucky, because many other variables that didn't know, that were on his side. And then risk, we say, or there is a high risk of going there. What is that? That means, like, there are factors which we don't know what will happen there, but there is a risk. And if you say what is the chance of happening this, chance and odds, even luck, all of these things are interpreted as uncertainty. Okay, and if you ask me what is the probability of an event, so we even write in mathematics what is the probability, assign the numbers, probability of this happening. Okay, or probability this won't happen, something like this. So that's what probability theory deals with. So in mathematics it's called probability theory. Now there are two schools in probability theory, two schools of thought we'll call. I think this is the first time you will be hearing a lot of detail about the probability in this sense, and otherwise people directly start with what is the event experiment. I don't want you to feel that this mathematics again is created by some other folks which were not interested in the real world. They tried to solve the real world problems by mathematics. Okay. Now there are two approaches to probability, two school of thoughts. The first school of thought is, we call it frequent test approach, or frequent test probability. So what is this frequent test approach? So here what you do is, so you analyze the frequencies of, like, there are two things. There are like favorable events, it will happen, and out of total events, how many times it will happen. Let's suppose you are tossing a coin, the only possibility is head or tail. Let's suppose the head or tail is a possibility, and you keep on tossing it, you keep on tossing it, let's suppose for 1000 times. And what you see is, you see that around 499 times it was heads, and around 501 times it was tails. Okay, if you keep on doing it, let's suppose to 10,000, 20,000 times, you will get it nearly 50% chance. This is what frequent test approach is. The events are observed and counted. Okay, they are observed and counted, and the frequencies provide the provide us the tools by which we can calculate probabilities. Okay, here you said that had appeared 499 times out of 1000, so you gave it a probability of 49.9%. Even if you conduct an experiment for, let's suppose, 10,000 or even 100,000 times, you will see that by frequent test approach it will give you numbers, and you will say, let's suppose 50% of the time this will happen. So what is the frequent test approach? If I write it in the words, so frequent test approach basically, events are observed and counted. So events are observed and counted, because now we have lack of knowledge. That's what I said, probability means lack of uncertainty. So let's suppose you are now hitting a coin, and you don't know what head will appear or tail will appear. Why don't you know? Because there are a lot of things, a lot of possibilities. But if you know, for example, the coin has this much weight, Okay, the pressure in the room is this much, and I'm hitting the coin at with this force. The point of contact with the coin is this much. You know all of these factors. Probably you can use the classical physics and you can accurately say whether it will be heads or tails. Okay, so if you know all of these factors, pressure of the pressure of the room, temperature of the room, point of contact, force with which you hit, weight of the coin, and the maybe surface area of the coin, everything you know about the coin, and then you can come up with a mathematical model or a physical model which by which you can say whether it's a heads or tails. You can say it with certainty. Now we assume that we don't know all of these factors. Okay, we don't measure all of these factors before tossing the coin. Then we consider this event to be uncertain because we don't know what will happen. So one approach is that the probability basically means lack of knowledge. We don't have knowledge of everything that is around us, and we call it a probabilistic event, an uncertain event. So now what we'll do is the first approach that the mathematicians provided. They said do one thing. You do these events continuously because sometimes there is no way of knowing all the factors that affect a thing. So now what they said is they said now you do these events, and you observe this event and you count the events, you count the total events that you are doing, and then you see the frequency that you wanted out of the total events, and you can, that's why you might have heard number of favorable outcomes, let's say number of divided by number of total outcomes gives the probability. This is what a frequentist approach says. Okay, how many of you are clear with the frequentist approach now? So now the second approach, the second model of probability, or we can say second school of thought, is called as Bayesian probability or Bayesian approach. Like they are really beautiful. Please focus here. So the second school of thought is called as Bayesian probability. Really important. So how I would like to introduce this topic is I'll give you something and you'll have to tell me, you'll have to answer me basically. I'll ask you a question and you'll have to answer me, and I'll see which probability approach will you use. Okay. So let's suppose we have a person. Let's suppose we have a person, and I'll give you some characteristic traits of this person. And I'll tell you, tell me who this person is. So the person basically is he likes a lot of detail, likes a lot of detail. Okay, and then he is alone most of the times. Likes to read books. Okay, and one more thing that I can say is he has less interest in people. He has less interest in people. Interest in people. These are some qualities I described about this person. Let's suppose this person is some person X. Okay, so the question now I'll ask you is this guy a farmer or a librarian? Okay, now I want you to tell me, is this guy a farmer or librarian? We'll have a discussion. The second example I want you guys to focus on. So let's suppose there is a COVID test which is 99% accurate. That says that if you perform test on 100 people, for only one person it will get it wrong. Okay, this is what COVID test is. Then let's suppose a person is tested for COVID. A person is tested for COVID and he got the result as positive. So I'm asking you, how likely is it? What is the probability that the person actually will be COVID positive? That's the second question. In the first example, if you see that, maybe all of these things that you said, like he knows a lot of, he likes a lot of detail, he reads books and has less interest in people, they hint towards the librarian. Let's suppose this description fits to the librarian, and he has the chances like of being librarian. Let's suppose 80% chances are that then this description is of a librarian. But you missed out an important fact. The fact is that there are more farmers, way more farmers than librarians. Okay, that is what we call as prior belief. What's the belief that we had? In the second example, when I asked you that this COVID test has 99% accuracy, and a person got tested as positive, some of you said 1%, 100%, 100%, 50%. So again, you missed one fact here. The one fact here is what was the prior chance of COVID. So you know that it was 0.01% nearly. So if you incorporate this information, Like out of 1,000 people, only one person has COVID. Out of 1,000 people, only one person had COVID. So even if this test is 99% accurate, let's suppose we have 1,000 people. Now I'll try to quantify it. We have 1,000 people in here. Now this COVID test is 99% accurate. Okay. So for how many people will it get the answer as wrong? That is 1% the people. So 1% is, I think, 10. So for 10 people, it will get it wrong. Even only 1% had the COVID. So it got it wrong for 10 people. Did you see now? Did you see what's the problem here? So even it has 99% accuracy. If you tested these 1,000 people, out of these 1,000 people, we had this prior belief that only one person will have the COVID. Okay, 0.01. And now you saw that it will get it wrong for 10 people. Okay, let's suppose it got wrong for 10 people and it considered 10 people to be, let's suppose, COVID positive. And now we have this 11th person. Okay, this actually has COVID. Okay, and what's the chance that his COVID is? Now you will see ki it drastically decreases because it is getting it wrong for 10 people and only one person has COVID. And by wrong I mean that it'll say these people have COVID. So it'll actually predict, let's suppose, 11 people have COVID, but only one person has COVID. So what's the probability that the test is accurate? It will be 1 by 11, let's suppose. So what is 1 by 11? So if you use the frequent test approach, so 1 divided by 11 is like nearly 0 point, like some 9% or something like that. Okay, so it will be 9% or something. You saw why is it 9%? The thing is, we had some prior belief. This is called as prior belief. Prior belief, that is what we saw from the data. So from the data we saw that out of 1,000 people, only one person had COVID. So if you perform this test on all 1,000 patients, okay, 1% times it will get it wrong. 1% basically means like for 10 people it will get it wrong. Even I think even more than that. If you see, for 1,000 multiply it by 0.1, 0.01, I think it's 10, right? So for these many of people it will get wrong. Like calculations can be here, and you can just adjust the calculations. You are seeing it right here that for these many people it's the test is getting wrong, and we'll say, let's suppose it's 0.1%, just to adjust it. Or we cannot even give a number, we can directly say that 1% out of these have COVID, and 99% accuracy means 100,000 people, and then we'll have it 1 by 100, and this is 1 divided by 100. I want to make these calculations accurate. Yes, 10 people. We're right. So we are saying that out of these 1,000 people, 10 people will be mispredicted, because that's what this test says. Because test will get wrong 1% the times, and now you see that in total only 1% had COVID, but you saw this 10 people it got wrong. So in total now it predicted, let's suppose, 11 people have COVID. So what's the possibility of this guy being actually COVID positive? Because total people it will detect COVID is for 11 people, but only one will have it. So 1 divided by 11 is the probability. That's nearly 9%. So how many of you understood this example, that by having this prior belief, you don't actually, if you incorporate this prior belief, you now update on seeing this test as positive, you don't change the whole belief that you had. You will just update your belief. That's what Bayes said in total. So Bayesian probability basically is a probability which is based on prior belief. So what he said that the approach to the probability is the events are assigned based on the evidence and prior belief. Okay, so what's the second approach? It says that you will have to have some prior belief, and on checking, this is the first thing, and on checking some evidence, you will assign the probabilities. You are not using a frequent test approach now. You are not seeing, okay, I did this, and out of these my favorable events were this much, and then out of these events this is the probability. So how many of you understood what's the difference between frequent test and Bayesian approach? I hope that you understood both of these approach, the frequent test approach and the Bayesian approach to the probability. And now we'll see, why do we read in machine learning? Why? I always like to answer why question of this. Why probability in machine learning? This is a question I want to answer. And in this we'll see what are the algorithms and where the probability is actually used, so that you actually know where this probability will be used in our next chapters. The first thing is that there is uncertainty in machine learning. I'll just write one heading, that is uncertainty in machine learning. Okay, So what is the uncertainty in machine learning? And let's suppose you even don't sometimes know what is the features to collect, because you are not domain experts. Okay, even if a domain expert is there, he doesn't still know. So why is there this uncertainty? Okay, this uncertainty can be because the noise, maybe, probably, let's suppose some noise came in the data. Okay, we'll have a separate heading for this. So the first thing that you can say is that I don't know what features to use, because sometimes you don't know how many features to. With these features, they're uncertain to you. You sometimes can say I'll use 10 features, then sometimes you can say I'll only use 9 features, and it is better to use more and more features, and this taking these features is uncertain. And the second thing is, what is the algorithm that I'll use, the best algorithm that I'll use, this again is uncertain. Okay, and the answers to these questions are unknown, basically what features to use, if you are, because you don't know what impacts what, and you try to till, let's suppose, to 90% accuracy, try to capture all the features. You're saying I'll use this features because I believe that these are the features which impact a thing. Okay, maybe there are some other features that you don't know of, and you are not capturing the information, and you see there's an uncertainty, and what algorithm or what model to even use, you're uncertain about that also. Okay, there's the first thing, there is inherent uncertainty in machine learning. That's why we use probability to capture or to deal with this uncertainty. The second thing is noise in the observations, which I was just talking about before this, noise in the observations. So what's the meaning of this noise in the observations? So I'm saying, even when you collect data, so we had this running example where we're looking at the iris data set, in which we had 4 types of flowers, 3 types of flowers: iris setosa, iris versicolor, and iris virginica. We had these 3 types of flowers. So just to reiterate, a side note, so we had this iris data set, so in which we had 3 types of species: setosa, versicolor, and virginica. I'll write it v dash. Okay, then we had 4 features: sepal length, sepal width, petal length, and petal width. Okay, these are our features. The first thing I said is uncertainty is that because you don't know if only these are the 4 features which impact the species. There can be other features also. Okay, there can be color probably, which we never saw. There can be, let's suppose, fragrance, which we never took as a feature. Okay, and these are our best possible features. We said, okay, on with these style work, and now there's the uncertainty in the features. After that, we have to use the algorithm. Now you don't know which algorithm will perform better, and there's an uncertainty in choosing the algorithm. The second thing I said is there can be noise in the observations. What is the meaning of that? That means that, let's suppose, you measured something and there was an inherent problem with the measure equipment tool. Okay, the tool that you had, the measuring tool you had, it had some problem, or due to some human error when you were writing down these observations, there was there's some problem. And a lot of things can happen due to which we can capture the different observations. Let's suppose you have to write 5.6, you accidentally wrote 5.06. Okay, this is the noise in the observation. Sometimes you have to write 5.6 and you wrote, let's suppose, 50.6, something like this. Okay, and you have to sometimes label this as one species and you wrote some other species, and you can incomplete, like, have this noise in the observations. And this noise can be because of human things or because of the tools error, whatever you have, and this noise can be there. Now it again, we have the uncertainty. The other problem, the other thing where the where we have why we would like to use this probability in ML is that we have incomplete domain coverage. Incomplete domain coverage. So what's the meaning of this? So meaning of this is, because you now do not know all the flowers that exist in the world. Okay, so still you have to only work with samples. You take just a sample size, that is by definition incomplete. Okay, sample by definition is incomplete. So if you take a sample, let's suppose, of 100 flowers, because now based on these 100 flowers, you're assuming that these 100, they represent the population. Whatever the properties these 100 have, they represent the population, but you never know, this is incomplete. Okay, so it may generate some bias, and it will create a model, and even you may not capture whole the variance, whole the variety of the people. Even I gave the example multiple times. When you see this Nokia example, when the machine learning model was trained on only the European people, they only captured a subset of the people, and basically the information was incomplete. That's why incomplete domain coverage. So whenever you are dealing with the sampling and things, and by definition you are capturing the incomplete information, you still have no uncertainty. Okay, so now to manage all of these things, there are other things that I can just pen down, but these are the important things that I would like you guys to know it. Why are we using probability? Why is probability so much successful in machine learning? This is because of this. Now to manage this uncertainty, we came up with this. We came up with the tools of probability. The probability theory was developed by mathematicians. Okay, it had nothing to do with teaching machines how to learn, but having these inherent qualities in machine learning. Okay, So if you had these properties in machine learning things, so the information is incomplete, there is noise in the observations, you don't know what features to take, there is a lot of uncertainty in this. So to handle this uncertainty, we are using the probability that mathematicians develop in the machine learning. Is it clear?
Yes, sir.
Okay. Now, why would we learn it? Why will you use it? The first thing, if you see it, why will you use it in machine learning is, so if you have to first, you have seen that KNN. We have something called as probabilistic KNN also. So if you have to predict a class, so you have to predict a class 0 or class 1, let's suppose. You'll assign a probability. You'll say there is a chance of 80% being in class 1 and 20% being in class 0. Whatever has the higher probability will assign that class. It's again probabilistic. So where we'll use it, the first is class membership. If you ask, we can use probabilistic class membership. Probabilistic class membership. So why does a particular example or instance belong to? So there we can use these probabilistic models. The second thing, some algorithms are inherently probabilistic. Some algorithms are inherently probabilistic. So probabilistic algorithms. So they deal in the, like, they are based on the probability itself. So we have probabilistic algorithms. So for example, we have an algorithm called as Naive Bayes. Naive. Sorry for the spelling mistake. So I'll change the color. So Naive Bayes algorithm. This algorithm itself is an algorithm which is based on the probability. Okay. Then we have something called as probabilistic graphical models. Okay. We have probabilistic graphical models. These are also based on probability. Then we have something called as Bayesian belief networks. Bayesian belief networks. These are inherently based on probability. Okay. And there are some algorithms on probability. Like, this is the first thing is we can assign this classes. This is probabilistic class membership algorithm where we can just assign these probabilities to classes. Then second, I said some algorithms are inherently probabilistic. The third thing I'll say is like models are sometimes used. They are trained by using this probability. So we can train the model by using probability. Okay, so I'll write it here. Probability frameworks are used to train models. Are used to train models. So what are the different algorithms that we'll use? There is something called as maximum likelihood estimation, MLE. This is one of the algorithms we'll use. This is the probabilistic algorithm. You see it, likelihood, maximal likelihood estimation. And then there is something called as EM algorithm, expectation maximization algorithm. So all of these things, all of these tools in the probability, they are used to train the models. Okay, this is where we use probability. And one more thing that I'll say is sometimes we use these probabilistic models to tune the models. So here we'll train models. In the second scenario, we'll tune them also with probability. Fine tuning means if you get a result and then you'll use probabilities, and even you can use probabilities to evaluate models. Okay, and these are the things that will be doing by using the probability. The first thing is you can use probability. There is this probabilistic class membership. So here you can assign classes some probability. What is, for an example, what is the probability it belongs to class 0? And but there are some in the next example, is this is the first example. The next example, there are some algorithms which are inherently probabilistic, like naive Bayes. There are probabilistic graphical models, Bayesian belief networks. All of these are probabilistic in nature. Then the other example I gave is the third example. I said probabilistic frameworks or probability frameworks. They are used to train models. For example, MLE is there, and you will heavily use this MLE, maximum likelihood estimation. Okay. Then we have EM algorithm, expectation maximization algorithm. These are used to train the train the machine learning models. Okay. And the fourth example I said is, if even if you have a model, you can still make it perform better. You can fine tune the model by using the probability concept, by using the frameworks of the probability. And the fifth thing is we can evaluate the models. We can use the probabilistic things and probability tools to measure the evaluation of the model. Okay, I hope that you saw where we'll use probability in machine learning. Is there a question?